In this chapter, we're going to look at the amounts of things in chemistry. When we look at a sample of a chemical, how can we count the numbers of atoms or molecules that are present in our sample? In the course of a chemical reaction, how can we keep track of the amounts of things present and predict the amounts of product we'll make? We're going to learn how to do all of that in this chapter. So let's start off by looking at an analogy for why we need to count things the way we do in chemistry. Let's say you worked at a hardware store, all right, and you had a customer come in and ask for a large quantity, a large number of really tiny things. Okay, so let's say you had these tiny hexagonal nuts that you're trying to count out. Okay, and these things are really fiddly. They're tough to pick up with your fingers and count individually. And besides, the customer wants 500 of them. Now, you could sit there and try to count 500 of them, and it would take you forever. So, what can you do instead that might save you some time? Well, you could count by weighing. You could say, all right, what's the mass of the average hex nut? You don't want to take one at random because maybe it's an unusual one. Maybe it's like, had a little bit of the metal flaked off of it, or perhaps it started to corrode and it's a little bit heavier with the rust. So you want to take a bunch of them and get an average. So let's say you count out 10 of them. Okay, that's a small number that's easy to count out. And you're going to get an average mass for them. So you weigh all 10. Okay, and you find out they weigh 105 grams, for example. And so then it's easy enough to figure out the average, right? To take the mean, you take that total mass and divide by the number. In this case, the average hex nut weighs 10.5 grams. Okay? Now, with that in mind, can we count out 500 hex nuts with that information? Well, the question you should then ask yourself is, how much do 500 hex nuts weigh? Okay, so you can kind of treat that average mass, 10.5 grams per hex nut, that's essentially a conversion factor. We saw this way back in the first chapter. We can use these numbers to convert between two quantities, right? So if we have 10.5 grams per hex nut, right, and we're starting off with 500 hex nuts, that's what we want to weigh out. Do we multiply or divide by 10.5? Okay, so think about how we'd get number of hex nuts to cancel out here. Okay, so think back to chapter 1 and think about how your units cancel out. So you probably would have figured out that we need to multiply, because if we take our 500 hex nuts, multiply by 10.5 grams per hex nut, you can see that the number of hex nuts here cancels out, and we get 5,250 grams. Okay, so now instead of counting out our 500 hex nuts, we just weigh out 5,250 grams and we give that sample to the customer. And that's it, you're done. Okay? So notice that counting really small things by mass is a lot easier than trying to count out individual things. In the case of chemistry, counting out individual atoms and molecules isn't just difficult, it's pretty much impossible. We're dealing with things that are so tiny that you can't really just pick them up and move them, right? So using mass to count numbers of things is very, very important. Okay, so this is where your periodic table kind of comes in handy here. You might notice that when we looked at our periodic table, in addition to the atomic number for every element, telling you the number of protons it has, you also see a decimal next to that element's symbol. Okay, now that decimal, of course, tells you the average atomic mass of that element. We talked about this back in chapter 3. Basically, if you take all of the isotopes of that element and take a weighted average of it, you get the average mass of an atom of that element. All right, so that's very useful when you are picking up or examining a sample of that element at random. Okay, so it's kind of the same reason why we took the average mass of a hex nut when we had our hardware store problem. Okay, now in your periodic table, these numbers are just written as a decimal and they're written kind of unitless. So when we're talking about individual atoms, or the average atom, we use atomic mass units, or AMUs. Okay, now, to put that into context, atoms are very, very tiny and very, very light. So one atomic mass unit is 1.66 times 10 to the negative 24 grams. Okay, we're talking about something very, very light. So instead of dealing with grams here when we're talking about individual atoms, we're going to work on the scale of atomic mass units. Okay. That being said, I might use this conversion factor here to help if we do want to convert between grams and so on. A little bit later on in this chapter, I'll show you a more convenient way to do this, to involve conversions between amounts of a chemical and its mass in grams. We'll get a much more convenient way of doing this. But bear with me for now. For now, we're going to stick with atomic mass units and use this conversion with grams. Okay, so as I pointed out, this is where those decimals in your periodic table are very, very useful. Okay, so keep that in mind. Those decimals next to your element in your periodic table give you the average mass of that atom. Okay, when you take into account all the isotopes of that element. Okay, so if you have a individual element, okay, and you want to figure out what is the average mass of this element, you can take that average atomic mass in your periodic table and realize you get a conversion factor from that. Okay, essentially it's telling you what the mass is of an individual atom. So for example, if you look up nitrogen in your periodic table, okay, so near the top right of your periodic table, you look for element N, and you'll see that the average mass of it is about 14.01 atomic mass units. Well, what does that mean? Well, that means that one nitrogen atom is equivalent to 14.01 atomic mass units, and that means we can write out two conversion factors. It's the same as saying there's 14.01 atomic mass units per nitrogen atom, or there's one nitrogen atom per 14.01 atomic mass units. Okay, so if we're trying to convert between numbers of atoms, nitrogen atoms, and the mass in AMU, we would use one of these two conversion factors to do that. Okay, so let's try a problem out and see if we can apply this. You have a 1 gram sample of lead. How many atoms of lead are present? Okay, so let's think about how we want to set this up. We are starting off with grams. Our periodic table is giving us the number of atomic mass units for lead. Okay, so that relationship between atoms and atomic mass units. So we're going to need one more conversion factor, and that's between grams and atomic mass units, which I had a couple of slides ago. All right, so keep that in mind. Okay, so if you look at your periodic table, you'll see that the average atomic mass of lead is 207.2, which means one atom of lead, on average, weighs 207.2 atomic mass units. Okay, and of course, as I mentioned a couple of slides ago, I pointed out that one atomic mass unit is 1.66 times 10 to the negative 24 grams. Okay, again, bear with me, I'll show you an easier way to get through this in a little bit. All right, with these equalities in mind, think about how you would set up your conversion factors. You're starting off with 1 gram of lead, okay? And so in your next step, you want grams to cancel out, and that if you use this second conversion factor, that'll get grams to cancel out and give you atomic mass units. Well, now you've got atomic mass units. In your next step, you want atomic mass units to cancel out, and you'll be left with number of atoms if you use this first equality. And that will leave you with what you're trying to find out. You want to wind up with atoms as your answer. So let's set that up. Okay, so we're going to take our 1 gram of lead, divide by 1.66 times 10 to the negative 24 grams, because that gets grams to cancel out. And then we're going to divide by 207.2 atomic mass units per atom, because that gets AMU to cancel out. And that leaves us with atoms. So go ahead and plug that into your calculator. 1 divided by 1.66 times 10 to the negative 24 divided by 207.2. And you should work out to about 2.9 times 10 to the 21 atoms of lead. Okay, and of course, if that seems like a large number, well, it is, because even though 1 gram doesn't seem like a very heavy mass, you have to remember that atoms are very small. Okay, so you can fit a lot of atoms in 1 gram of that material. Okay, so again, that's kind of how you would do these types of calculations. It's a lot of this dimensional analysis that we covered way back in chapter 1. I think I pointed out back then that a lot of the math in this class involves just multiplying and dividing conversion factors. So when in doubt, pay attention to your units so you'll know whether you need to multiply or divide. Okay, so your units will always cancel out like this to get you the answer you need. Okay, let's try doing one backwards. We want to calculate the mass in atomic mass units of 1 times 10 to the 4 carbon atoms. In other words, 10,000 carbon atoms. Okay, so since we're dealing with carbon, you may want to look up carbon in your periodic table. Okay, if you haven't already pulled out a periodic table, I really recommend doing that. You're going to need it a lot in this chapter. Okay, so have a periodic table in front of you and look up carbon. Okay, so you've probably figured out that carbon has an average atomic mass of 12.01, okay, or 12.011, depending on how many decimal places your periodic table goes to. Okay, so do we need anything else besides this conversion factor? Well, the question's giving us atoms, and it's asking for the answer in atomic mass units, so we actually don't need any other conversion factors. We can just use this equality to determine the conversion factors that we need. So one of these two things is going to be the conversion factor we use. We're either going to multiply by 12.01 or divide by 12.01. Okay, so think about which one you want to pick. Okay, just as a little practice from that chapter 1 stuff about conversion factors. Keep in mind we're starting off with number of atoms, and we want atomic mass units to be left as our numerator, to be left as the answer. Okay, so you've probably hopefully figured out that you need the one on the left, right? We need atomic mass units on top here, and we need number of atoms on the bottom, so that atoms cancels out. Okay, so we take our 10,000 times 12.01 atomic mass units, and we get 1.2 times 10 to the power of 5 atomic mass units. Okay, all right. So that's basically how you would apply that. Use those conversion factors to go between mass and number of particles, in this case atoms. Okay, so far the examples we've used have just been elements. I used just the element lead, just the element carbon. Keep in mind, we can still apply this to compounds as well. Okay, all you've got to do to get the mass of a formula for a compound is to just add up the mass of the atoms making up that formula. Okay, so for example, let's say we wanted the formula mass of calcium chloride. Well, first of all, make sure you have the formula of calcium chloride. So think back to, a couple of chapters ago, back in like chapter, I think 4 or 5, where, oh yeah, I guess it would have been chapter 5, where we talked about the formula of ionic compounds, right? And calcium's a metal, chlorine's a nonmetal, that's an ionic compound. We figured out the formula must be CaCl2, right? Okay, so because calcium has a 2+ charge, chloride has a -1 charge. Again, you can go back to chapter 5 if you want to practice this or see where we're getting this number from. Once you've got that formula, though, getting the mass of that formula is really straightforward. You look up calcium in your periodic table, okay, and you see that it has an average mass of about 40 atomic mass units. You look up chlorine in your periodic table, and you see that it has an average mass of about 35.5 or 35.45, depending on how many decimal places you're going to. Okay, and then we're going to add these up. Now, the thing to watch out for is that there are 2 chlorines in your formula, so you actually have to double that contribution from chlorine. So we take our 40.08 atomic mass units, and we just use that number because there's only 1 calcium. With our chlorines, on the other hand, because there's 2 of them, we actually wind up doubling this number. So we get about 71. Okay. A quick note here about the numbers we're using. I've gone to 2 decimal places in both of these numbers. To be honest with you, you could pretty much round off to the nearest whole number for calcium. You could have just used 40, and you're going to get a close enough answer. It's good enough for multiple choice, at least, That being said, for something like chlorine, I wouldn't round this off to 35. 35.45 is far away enough from 35 that, I'd be a little hesitant to round it down that far. But I would use 35 and a half. I think that's a close enough approximation. In any case, when you get 70.9 here, uh, that's basically about 71. So, feel free to use that. Okay, but if we take 40 and add 71 to it, we get a total of 111 atomic mass units. Okay, or I've gone to 110.98 because I've gone to more decimal places. But again, if you got 111 by approximating, that's close enough. Okay, and that is the total mass of our formula of CaCl2. Okay, so anytime you have a formula, just take the masses of the elements making up your formula and just add them together. Of course, keep in mind if you have more than one atom of an element, be sure to multiply the mass by that number. Okay, so in this example, we multiplied chlorine by 2 because there were 2 chlorines. Okay, remember I told you earlier there's a shortcut to figuring out that relationship between grams and numbers of atoms or molecules or whatever? We don't have to use that conversion factor between grams and atomic mass units. This is where where I'm going to get to that. Okay, so to understand this, I first have to explain why we group things together. It's sometimes more convenient to count out things when you do that in bunches, right? Rather than counting out individual pieces of something, it's easier to count out groups. So for example, if you go to a bakery in the morning, and let's say you want to get donuts for your office, right? And you don't ask for like 36 donuts, right? You just say, oh, could I have 3 dozen donuts? Because the bakery probably has boxes that hold a dozen donuts, and they just fill up 3 boxes. It's easier to count that out than to individually count 36 donuts, right? Likewise, when you go to, let's say, Staples or Office Depot or whatever, and you're buying paper for your printer, you don't say, oh, could I have 10,000 sheets of paper? No, you just say, oh, I want to buy a ream of paper, right? You want to buy like a bundle of paper that has lots of sheets of paper. You don't have to count the sheets individually because you can buy the whole stack of paper, right? That's where counting things in groups becomes convenient, right? We can deal with large numbers of things and simplify them by just counting the groups of those things. Okay? And we totally take advantage of this in chemistry, because in chemistry we deal with lots of tiny things. It's kind of a pain to deal with them on an individual basis. You don't want to count individual atoms or individual molecules when you can count out moles. A mole is just a group word, just like dozen or or a ream or a pair or like any group word. A mole is just 6.022 times 10 to the 23 things. It's just a large number of things. So just like a dozen is 12 things, a mole is 6.022 times 10 to the 23 things. That's a really large number, of course, and that's why moles are very useful for counting large numbers of things, which we deal with a lot in chemistry because we're dealing with very tiny things. Now, saying the number 6.022 times 10 to the 23 over and over again is kind of a mouthful, so we sometimes refer to this as Avogadro's number when we're referring to the number itself. Amadeo Avogadro was the scientist who kind of figured out the math behind this. Okay, well, we'll see him again in the next chapter when we start talking about gases, because he was doing experiments with gases that he figured this out. Okay, but basically, you could think of this as the conversion, the number you need for the conversion between moles and numbers of particles. Okay, now I say particles because we can apply this to anything. Just like you can use the word dozen with anything. For example, you could have a dozen donuts, you could have a dozen eggs, you could have a dozen people. In the same way, you can have a mole of atoms, you can have a mole of molecules, you can have a mole of ions. You see where I'm going with this, right? The word mole is very versatile like that. Okay, so I mentioned here that there was a shortcut that's going to come in handy for relating mass with numbers of things, right? Earlier we we related numbers of atoms or particles to the mass in atomic mass units, and if we wanted to get to grams, we had to do another conversion between atomic mass units and grams. Well, here's the thing with moles. 1 mole of an element happens to weigh its average atomic mass, but in grams, not in atomic mass units, right? So it essentially lets, if we scale things up on moles, in terms of moles, we can essentially weigh stuff out in grams instead of atomic mass units, which makes things very, very convenient in a lab. But, you can't weigh things out in atomic mass units in your lab, but we can weigh things out in grams very easily. And since our masses in our periodic table, our average atomic masses are essentially scaled up from atomic mass units to grams now, it makes counting things out very easy if we deal with things in moles instead of just individual particles. That being said, sometimes we do want to get to individual particles, and moles are kind of that middleman that help us relate numbers of particles to grams. We'll wind up doing calculations for all of these conversions, and I'll go through some examples in a little bit. But first, let's start off with an example that looks just at that relationship between moles and numbers of particles. So here, in this question, how many molecules of bromine are present in 0.045 moles of bromine? Okay, so here we're not using grams at all or mass in any way. We're going from number of particles, our molecules, and we're starting off with moles of that chemical. So we're starting off with moles of bromine and trying to get to molecules. So remember, the conversion factor that ties this together is Avogadro's number. That tells us how many things are in a mole. All right, and in this case, the things we're trying to get is molecules of bromine. Okay, so we know that 1 mole of bromine is Avogadro's number of molecules of bromine, the number of particles in this case, right? So we can get 2 conversion factors from this. We could say that there are Avogadro's number of molecules of bromine for every mole of bromine, or that for every 1 mole of bromine, we have Avogadro's number of molecules. So think about which of these 2 conversion factors we want. Remember, we're starting off with moles here, so we want that to cancel out and be left with molecules. So you've probably figured out, hopefully, that it's the conversion factor on the left that we're going to use. So when we set that up, we take our 0.045 moles of bromine, and we're going to multiply by Avogadro's number, and that gets moles of bromine to cancel out, and we get our answer in molecules. 2.7 times 10 to the 22 molecules of bromine. Okay. Please note, by the way, notice that moles don't have to be in whole numbers. They can be decimals as well. Okay, which is, again, we do that with other counting words as well. If, you could ask for a half dozen donuts, for example, or a half dozen eggs at a grocery store. Okay, you don't have to buy things by the dozen necessarily. Okay, so in the same way, we don't have to have a whole mole of something. We could have 0.045 moles. Okay, and it still helps us count out. It's easier to write down 0.045 moles of bromine than say that we're dealing with 2.7 times 10 to the 22 molecules of bromine. All right. That being said, of course, sometimes we do need numbers of particles. Like in this case, we wanted to calculate the number of molecules we were dealing with. Okay, I'll get into some more examples of these types of conversions when we're kind of summing up this section. Okay, so we'll come back to this concept in a little bit. Okay, so far we dealt with just an element there. Keep in mind, of course, that we are using compounds as well, and you've got to think about how you want to relate your molar mass, your formula weight, and things like that to your whole formula. Okay, so when we look at the formula of a compound, so far we've taken that to mean that in 1 unit of that formula, those subscripts tell us the number of atoms that we're dealing with, right? So for example, when we look at, at our earlier example of calcium chloride, there were 2 chloride ions for every 1 calcium ion, right? But we can scale this up when we're dealing with moles. So if we had a mole of calcium chloride, there would be 1 mole of calcium ions and 2 moles of chloride ions. To use the example here on this slide, if we have a molecule of glucose, 1 molecule of glucose, which is a covalent molecule, we have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. That's why the formula is C6H12O6. But we can scale that up. If we have 1 mole of glucose, we have 6 moles of carbon, 12 moles of hydrogen, 6 moles of oxygen. You see? Now, remember how earlier I said you don't have to necessarily deal with whole numbers of moles. You could deal with decimals, just like you can deal with decimals when it comes to other counting words, that you can have half a dozen. In the same way you could have half a mole if you wanted to, or any decimal. Well, let's look at an example where we scale up or down accordingly. So how many moles of carbon atoms are present in 1.85 moles of glucose? Okay, so think about what's the relationship between carbon and glucose. Our formula of glucose, of course, was C6H12O6. Okay, so we want to look at that subscript of carbon specifically in that formula of glucose. So the formula is C6H12O6. That tells us there are 6 carbon atoms in every molecule of glucose. But if we scale that up, there are 6 moles of carbon in every mole of glucose. And since we're dealing with moles here in the question, that's kind of why we're talking about moles of carbon. So essentially, there's 6 moles of carbon per mole of glucose, or if to put the other way, for every mole of glucose, there are 6 moles of carbon. Now, please note that we're starting off with moles of glucose. So ask yourself which of these two will get moles of glucose to cancel out. Well, notice that this one has moles of glucose on the denominator, right? So we're going to pick that one. So we take our 1.85 moles of glucose, multiply by 6, okay? And that gives us our number of our moles of carbon atoms. We have 11.1 moles of carbon, okay? Notice that we didn't have to deal with counting numbers of carbon atoms here. We're still using that group word, moles, to describe our amount of carbon. Okay, so please be careful of how the question's phrased. Since the question here is asking for moles of carbon, we don't have to use Avogadro's number at all in this problem. Okay, but keep in mind, they could have asked a follow-up question. They could have asked how many carbon atoms are present, in which case you would then take this answer and multiply by Avogadro's number. Okay, so keep that in mind. Avogadro's number is that conversion between moles, as you're showing here, and numbers of things. Okay, so I mentioned earlier that, again, like one of the really convenient things about dealing with moles here is being able to relate it to the mass of something in grams. Okay, and to be honest with you, we're dealing with this pretty much the same way as we did with atomic mass units. We can use the average masses in our periodic table for our elements and get a conversion factor that deals with grams into moles. Okay, so essentially, instead of using atomic mass units per atom as our conversion factor, just realize those numbers in your periodic table, those decimals, are in grams per mole. Okay, we're just picturing different units, but the numbers themselves are the same. Okay. So whenever you add up the masses of your, your elements in your compound, what you're doing, instead of just getting the mass in atomic units of one molecule of that substance, you're really getting the mass in grams of 1 mole of that substance. Let's take water, for example. Water has the formula H2O. Okay, now if you look up water in your periodic table, hydrogen is approximately one atomic mass unit, and oxygen is about 16, right? So since there's 2 hydrogens in H2O, 1 plus 1 plus 16 gives you 18 atomic mass units. So an individual water molecule, on average, weighs 18 atomic mass units. But again, like I said, those numbers can scale up. 1 mole of hydrogen atoms weighs 1 gram. 1 mole of oxygen atoms weighs 16 grams. So if we have 1 mole of water, it would weigh 18 grams. So here in this sample of 18 grams, we actually have 1 mole of water molecules. So there's Avogadro's number of water molecules present in this sample of water. Okay. So that being said, trying to calculate your formula weight is the same. You just take your mass from your periodic tables for the elements making up your formula and just add them together. Just the same way we did the formula weight in atomic mass units. So the only difference here is that we're using grams instead of atomic mass units, but the numbers are exactly the same. Okay, that's the convenient thing about this. All right, so let's try a practice problem here. Let's say we wanted the molar mass of iron 2 sulfate. Now, what do I mean by molar mass? It's essentially the formula weight. It's just the units are grams per mole. And as I pointed out, since the numbers are the same, we're just using grams instead of atomic mass units. You're really not doing anything different. You're still adding up the same numbers. Okay, so the formula of iron 2 sulfate is FeSO4. So go ahead and look up, using your periodic table, the mass of iron, sulfur, and oxygen. Now, don't forget, there are 4 oxygens here. Okay, notice that subscript 4 only applies to the oxygen. Okay, there's 1 sulfur and 1 iron. So with that in mind, see if you can find the total mass of this formula. Okay, so feel free to pause this video if you'd like, but when we come back, here's the answer. So if you looked up in your periodic table, iron is 55.85 grams per mole, sulfur is about 32, and oxygen is about 16. Okay. Again, I think you could round off to 32 and 16 for oxygen and sulfur, or sulfur and oxygen respectively. Iron, I guess you could round that off to 56. It's probably close enough. So if you rounded that off to 56, that's fine. Again, if you want to leave it at 55.85 to be a little bit more precise, that's also fine. It's just a few extra keystrokes, so it's up to you. But again, let's add these up. But again, keep in mind that there are 4 of these oxygens. So you're actually going to take the 16 and multiply by 4. Okay? So when we do that, we actually get the numbers for iron and sulfur remain the same, but our oxygen contribution is actually 64 grams. So when we add that up, our total mass is 151.85 grams, or 152 if you used 56 for iron. All right, so that's how you figure out the molar mass of your compound. So that's how many grams 1 mole of iron 2 sulfate would weigh. Okay, so if you had you weighed out 151.85 grams of iron 2 sulfate, you would know that there are Avogadro's number of formula units in there. Okay, so just to sum up what we're trying to do here, okay, because this is the bulk of the types of conversions you're going to see, and I really recommend practicing this, just getting the hang of converting between these units, because if you can get this to be second nature, it's going to make a lot of these calculations a lot simpler and easier for you, not just for this chapter, but you'll see that we're going to do very similar types of conversions into and out of moles in the subsequent chapters as well. Okay, you're going to get very, very comfortable with this. So if it's a little bit of a struggle now, because moles is a new word for you, don't panic. You're going to get better at this. But my advice is to do as much practice as you can, and you'll find that the more you practice it, the easier it becomes. Okay, so what we're dealing with here is 3 main quantities that we're converting between. We've got numbers of particles, okay, which particles can be, atoms, molecules, ions, whatever, okay. We're dealing with moles, so number of moles, and we deal with masses in grams, okay. We're not going to deal much with atomic mass units. Grams are more convenient, to be honest with you. So you might see the occasional calculation involving atomic mass units, but quite frankly, most of your calculations will involve grams. That's just how we weigh things out in a lab. So, grams are just really convenient that way. Okay, so get comfortable with those 3 types of converting between those 3 quantities, and just realize that you have different conversion factors for each of those conversions. So, if you want to convert between moles and number of particles, you're going to use Avogadro's number. That's the conversion factor that gets you between moles and number of particles. Likewise, if you want to convert between moles and grams, you want to use the molar mass of that substance. Okay, because again, the units of molar mass is grams per mole. It's what ties together grams and moles. Okay, so you want to use that as your conversion factor between those two things. Now, whether you multiply or divide depends on which way you're going on in this conversion, right? If you want to get from, if you want to get into moles, usually you have to divide by something. So if you have grams of a substance and you want to get moles of that substance, you divide by the molar mass. Likewise, if you have particles of a substance, like number of atoms, you would divide by Avogadro's number to get moles of that substance. And vice versa. If you have moles of a substance and you want to get grams, you'd multiply by the molar mass or multiply by Avogadro's number to get the number of particles. Okay. Don't stress about memorizing that because, again, if you get the hang of dimensional analysis that we covered in Chapter 1, if you get comfortable with seeing your units for the numbers you're dealing with and thinking about, okay, would I multiply or divide here to get these units to cancel out? That will help you remember whether you multiply or divide. Okay, by looking at whether your units, how can you get your units to cancel out? Okay, that's the key thing you want to see here. Again, the more you practice this, the less you actually have to think about it. It becomes just sort of automatic. All right, so I really cannot stress enough that you really want to practice this stuff. Okay, so let's try some examples. And again, this is what I was talking about earlier about that convenience of converting between, of dealing with moles to make it easier to convert, between grams and moles to help count things out. Okay, so we have 3 milligrams of sodium chloride. How many moles are present in this? So we have 3 milligrams. We're trying to get to moles. Now, we're told the chemical we're dealing with. We're dealing with sodium chloride, or NaCl. Okay, so if we're going between mass and moles, well, first of all, let's get our mass in grams. So instead of milligrams, we're going to divide by 1,000. So we're actually dealing with 0.003 grams of sodium chloride. We want to get to moles of sodium chloride, so we're going to need the molar mass of sodium chloride. We're dealing with grams, right? Where the question gives us grams, essentially. We want to find moles. That's what we're trying to find out. So we need a conversion factor that has grams and moles in it, specifically dealing with sodium chloride. So we look up sodium in our periodic table. It's about 23 grams per mole, right? That's what that decimal of 22.99, if you want to round it off to 23, that's totally fine. And chlorine is 35.5, or so. So when we add that up, we get a molar mass of about 58.5 grams per mole. Okay. So again, I've kind of gone a little bit more precise, but if you wrote 58.5, that's close enough. Okay. So that's how many grams 1 mole of sodium chloride weighs. All right, but we've got 0.003 grams. How many moles is that? Would we multiply or divide by 58.44? Now remember, we're starting with grams here, and we want grams to cancel out. So we probably want to divide by grams, right? So if we look at our two conversion factors, this one on the right here gets grams to cancel out. So we divide by 58.44 grams per mole, grams cancels out, and we figure out our number of moles of sodium chloride. Okay, there's 5.13 times 10 to the negative 5 moles of sodium chloride. You probably, if you used 58.5, you wouldn't have got exactly this number. It might have been a little bit smaller, which is fine. It's okay if you have a little bit of rounding error here. Again, it's good enough for multiple choice, so something to keep in mind. Okay, here's another problem. Why don't you guys try this one out? Feel free to pause this video and take a crack at this. Okay, but we've got 3.86 times 10 to the negative 20 grams of this of ethylene glycol, antifreeze, and we're trying to figure out the number of particles. Okay, the number of molecules here. Quick note here with this problem. If I go back here to our previous slide about our conversions, notice that there's no direct way to go from particles to grams or vice versa. These are not tied together. you have to go from moles via moles as sort of your middleman between those two. Okay, so in the question we're about to do, they're starting us off with grams. We'd have to convert to moles, and then from moles to number of particles. Okay, so something to keep in mind that there's going to be more than one step involved here. Okay, so starting off with grams, we want to convert to moles. So keep in mind that we use molar mass for that, like we did in the previous problem, right? Grams per moles. And then we're going to use Avogadro's number to get to number of particles. Okay, so if in order to proceed with this, we need the molar mass using this formula C2H6O2. So use your periodic table, look up the masses of carbon, hydrogen, and oxygen. If you, for some reason, don't have a periodic table in front of you, I'll tell you that carbon is 12 grams per moles, hydrogen's 1, and oxygen is 16 grams per mole. Okay, but please note that there are 2 carbons, 6 hydrogens, and 2 oxygens. So add this up accordingly. So if you did, you would have gotten about 62 grams per mole. These numbers weren't exactly what I told you. So like if I go to more decimal places, you can see there's a little bit of rounding that's a little bit different from yours if you got 62. But again, if you use 62, that's going to be close enough. Okay, so we're either going to multiply or divide by that molar mass to get the answer. Okay, now it's not the final answer. It's just going to give us the number of moles of ethylene glycol we're dealing with. Of course, then with that answer, we're going to either multiply or divide by Avogadro's number. Okay, so we're either going to multiply by Avogadro's number or divide by Avogadro's number, and think about which one we'd want to use to get rid of moles, because we're going to be, we're going to have a temporary answer in moles here. To get to molecules, how would we get moles to cancel out? Okay, hopefully you'll figure out that we use the conversion factor on the left here. So I'm going to combine everything on one line here. If you want to break this up into 2 steps, you're totally welcome to. But I've done everything on one line here. Okay, so we started off with 3.86 times 10 to the negative 20 grams, right? That's what the question tells us we're starting with. We would divide by the molar mass. You can see here that grams cancels out. Okay, so then you would get your answer in moles if you were doing this in 2 separate steps. Of course, then in the next step, you want to multiply by Avogadro's number because that then gets moles to cancel out. And you would then get your answer in number of molecules, which in this case is about 375. Again, your answer might be slightly off from that, and that's okay if it's slightly off. Okay, so again, this is a good example for showing how we can use both of our conversion factors. We needed molar mass to get from grams to moles. Okay, in this case, we had to divide by molar mass in order to get the units to work out. And then to go from moles to number of particles, we'd have to multiply by Avogadro's number. Okay. All right, so that brings us to percent composition. Okay, so when we look at a sample of a material, we can look at what what percentage of that material comes from each individual element. Okay, now that we're dealing with masses here, it's easier to sort of figure this out based on mass. Okay, just a recap of what it means to have percent composition, or to look at the percent composition of something. Percent, just to jog your memories, is out of 100 in Latin, right? Percent. So whenever you're dealing with a percentage, you're really looking at what it is out of 100 of something. Okay, so it's like the number of specific items in a group of 100 items. Okay, to give you a really silly example, let's say you have 4 oranges and 5 apples. Okay, what percentage of that total piece of fruit is, comes from oranges? Well, 4 and 5 is 9 pieces of fruit. So we have 4 oranges out of 9 pieces of fruit. So we take 4 divided by 9 times 100, and we say our sample of fruit is 44% oranges. Okay. Now, the nice thing here is that we can scale that up accordingly. If we say we've got fruit that's 44% oranges, if we scale that up from 9 pieces of fruit, if we had 100 pieces of fruit, we would say, well, 44 of those would be oranges, right? The remaining, 56 pieces of fruit would be apples. So again, this is kind of just a silly example, but that's essentially how percentages work. The nice thing here is that we could then use that with compounds, but instead of actually counting out elements and things, because we know what the average atomic mass or molar mass of our elements are, we can just use those numbers in our periodic table to figure things out, to figure out the percentage of a formula that comes from each element. Okay, so all you've got to do is when you look at your total, your molar mass of your compound, ask yourself, okay, what's the mass that comes just from this element in question? Divide it by that total molar mass and multiply by 100 because it's a percentage. And that'll give you the mass percentage or percentage by mass of that element in the compound. Okay, there's a practical application of this that I'll get into in a second. Okay, but first let's practice figuring out percent composition from a formula directly. So let's say we have ammonium hydroxide. It's a compound, an ionic compound made of the polyatomic ammonium, NH4, with a positive charge, and hydroxide, which is OH minus. Okay, so the three elements present here are nitrogen, hydrogen, and oxygen. All right, so if we want to figure out the total mass of ammonium hydroxide, well, if we look up nitrogen in our periodic table, it's 14 grams per mole, and there's one of them. There are 5 hydrogens. Don't forget this 5th hydrogen over here in the hydroxide ion. Okay, so 4 plus 1 is 5. And each hydrogen's about 1 atomic mass unit, or 1 gram per mole, if we scale it up. So 5 of them is about 5 grams per mole. And of course, our 1 oxygen is 16 grams per mole. Okay, so again, I've gone to more decimal places here. But if you want to say 14, 5, and 16 respectively, that's totally okay. So we get a molar mass of 35 grams per mole. Okay, that means that if we had 1 mole of ammonium hydroxide, it would weigh about 35 grams. Okay, so what is the percent composition of each element in ammonium hydroxide? So if someone asked you, out of my 35 grams of ammonium hydroxide, what percentage comes just from nitrogen? Well, the nitrogen contributes 14 grams out of that 35, right? So to figure that out, I would take 14 grams from my nitrogen, divide by 35 grams for the total, times 100%. Okay, and I would get about 40% of nitrogen. Okay, again, my numbers here are going to be slightly off than if you use whole numbers. Okay, similarly for hydrogen, we need to take the mass of hydrogen that hydrogen contributes to this total and divide by 35. Now, do I take 1 or do I take 5? We have to take that total mass of all 5 hydrogens into account. So it's 5 divided by 35 times 100, which gives you about 14% of hydrogen. And then with oxygen, of course, we take our 16 divided by 35 times 100, and we get, about 45.65% oxygen. Okay. If you want to check your work, these 3 answers would add up to about 100%, give or take. There might be a little bit of rounding error. So if you get 99.99 or, 100.1 or something like that, that's totally okay, right? These things happen. Of course, you probably don't have to, a question will often ask for just one of these, okay? I just did all 3 just to kind of prove that the numbers add up. Okay, so that's basically how you can find your percent composition of an element from its formula. Now, that seems pretty straightforward when you're trying to do the math there. But here's the thing that makes this very useful. All right, there are instruments out there, specifically a technique called mass spectrometry, which will give you the percentage of each element in a sample. Right? So if you have a sample of a chemical and you put it in a mass spectrometer, it will tell you what percentage is present. Okay? So if I had a sample of ammonium hydroxide and I put it into my mass spectrometer, it would tell me, oh, you've got, about 40% nitrogen, 14 point whatever percent hydrogen, and 45.65% oxygen. Okay, that would be the data it would give me. So if I didn't know that I had ammonium hydroxide, I could use that information to figure out what I had. Okay, I could figure out that I had ammonium hydroxide because my mass spectrometer gave me these percentages. Now, how do we do that, right? How would I go backwards in this problem, going from percent composition into a formula? Okay, that's kind of a useful technique to learn. So in order to understand that, I'm first going to tell you about empirical formulas. Now, the funny thing is we've actually already talked about empirical formulas, except I just didn't point it out. When we dealt with the formulas of ionic compounds, we gave our ratio of ions in the simplest ratio, right? Well, that's what an empirical formula is. It's the simplest ratio of elements in a compound. Okay. Now, in the case of covalent compounds, though, sometimes you can simplify those ratios. Since a covalent formula tells you the number of atoms of elements in a molecule of that compound, sometimes you can reduce that ratio. Okay, so sometimes an empirical formula is not necessarily the same as the molecular formula of the compound. Okay, but in any case, I'm going to show you eventually how we can take our percent composition data and get our empirical formula from that. Okay, and then we're going to see how we can scale up our empirical formula to figure out the molecular formula. So to work through this, basically we want to get to moles, right? If a question starts off with the mass of a substance, right, that's essentially what we're getting from our mass or percent composition data. We're getting the percent by mass of our elements. We want to convert this to moles. All right, because once we have moles, we can compare things. It's like with moles, you're just dealing with numbers of things, right? And it makes comparing things easier. So that's the first step, essentially. You're going to convert your mass of your elements into moles using their molar mass, as we've already just learned. We're then going to just simplify that ratio, and that's basically your empirical formula. Okay, and I'll show you a math trick that'll make this simplification a little bit easier. Okay, if you're having trouble doing it. Okay, we'll go through an example in a little bit. Now, when it comes to expressing your empirical formula as a molecular formula, you need an extra piece of information. You need to know what the mass of your molecule is going to be. Okay, because that tells you essentially how much to scale up your empirical formula. Because we're going to compare the mass of our molecular formula, which is our molar mass. If we divide that by the mass of our empirical formula, we know how many times to scale up. Again, I'll show you this in an example and make it probably a little bit easier to understand than me just saying it. Okay. Of course, going backwards is really straightforward. If you're given a molecular formula and you're trying to find the empirical formula, you just simplify whatever ratio you're dealing with. Okay, so for example here with glucose, okay, our formula is C6H12O6. If we want to write out its empirical formula, we look at those numbers, 6, 12, and 6. What can we, what's the largest common factor that we can take out of these? Well, I guess that would be 6, right? If we, 6 goes into 6 once, 6 goes into 12 twice, and 6 goes into 6 once, right? So if we divide those each by 6, we have 1 carbon, 2 hydrogens, and 1 oxygen. So our empirical formula is just CH2O. All right, and so here our scaling up factor is 6, because we'd notice that the mass of glucose is 6 times heavier than the mass of this empirical formula of CH2O. Quick note here, by the way, it is possible to have an empirical formula be the same thing as your molecular formula. So for example, here I've got carbon dioxide. Carbon dioxide's molecular formula is CO2. Since there's only 1 carbon here, I can't really simplify that any further, right? It's not like I can divide 1 by something and get another whole number. 1 is the simplest whole number. So the empirical formula here is just going to be CO2 as well. Okay, let's try a practice problem out so we can see, so you can see what I mean by doing these, this process of going from our percent composition data to an empirical formula, and then from there to the molecular formula. All right. So we're told that lactic acid has percent composition data of 40% carbon, 6.71% hydrogen, and 53.3% oxygen. Okay, so if we put our lactic acid into a mass spectrometer, this is what it would spit out at us. Okay, now I'm also going to tell you that lactic acid has a molar mass of about 90 grams per mole. We'll get to that later. That's going to help us do that last conversion from empirical to molecular formula. So for now, we don't need to pay attention to that. Okay, now our first step, of course, is to get from grams to moles. The easiest way to deal with these numbers, since you're given percentages, is just assume that you have 100 grams of the material. Okay, because then all that does is that takes your percentage signs and converts them into grams. Because, well, what's 40% of 100 grams? It's 40 grams, right? 6.71% of 100 grams is 6.71 grams, and so on. Okay, so assume you have 100 grams of your sample, and so all these percentage signs become grams. Now, if we're dealing with grams, I mentioned earlier that we want to convert to moles. Once we have these numbers in moles, we can compare these elements. We can't compare the masses of the different elements because different atoms weigh different masses. A hydrogen atom is much lighter than a carbon atom. Okay, so we can't use grams directly. So instead, let's convert to moles. So I'm going to take my 40 grams of carbon, and I'm going to divide by 12 grams per mole for carbon, and that gives me my molar mass. Okay. Likewise, I'm going to do that with hydrogen. I'm going to take my 6.71 grams of hydrogen, divide by the molar mass of hydrogen, and I get, basically about 6.71 grams moles of hydrogen. Looks like here I've used 1.008, but again, if you used 1, you're going to get a close enough answer. Okay. Likewise with oxygen, we're going to divide by 16 grams per mole, and we get the moles of oxygen. Okay, now we have our moles of our three elements. We have 3.33 moles of carbon, 6.6 whatever moles of hydrogen, and 3.3 moles of oxygen. Okay. Again, if you don't have exactly these numbers, because like I said, if you used 1 gram per mole of hydrogen instead of 1.008 grams, your numbers won't be exactly the same here, but probably close enough. The problem you've probably picked up right now is you've noticed that these are all decimals. And furthermore, these decimals are quite a bit off from the whole numbers you would hope for. Okay, so 3.33 is significantly higher than 3. If you had like 3.1 or 2.99, I could round that off to 3, no problem. But 3.33, that's kind of a bit off from 3. Okay, we can't simply round these numbers off to whole numbers. They're just too far from whole numbers. So this is I'm going to show you now this math trick I was talking about that can help you simplify this ratio into a whole number ratio, because that's what you need. You're going to need whole numbers for the subscripts in your formula. Okay, so how do we convert this into a whole number ratio? The answer is we're going to pick the smallest of these numbers. Now it happens that there are two numbers that are equal that are the smallest, and that's 3.33. Okay, so we're going to take that smallest number, 3.33, and we're going to divide everything by that smallest number. Okay, so I take my 3.33 moles of carbon, I'm going to divide by 3.33, and that gives me 1 mole of carbon. I'm going to take my 6.66 moles of hydrogen, divide by 3.33, and that gives me 2 moles of hydrogen. Now, by the way, if you had 6.71 here and you divide by 3.33, you're not going to get 2 exactly. You're going to get a little bit more than 2, but it's going to be like really close to 2. So it's probably close enough that you could round it off to 2. Okay. And then, of course, with our last one, 3.33, when we divide that by 3.33, we get 1 mole of oxygen. Okay, my point here is that by dividing everything by that smallest number, you oftentimes get a whole number ratio. Now, even this sometimes doesn't work perfectly. Sometimes you're going to get numbers that aren't whole numbers, that again are a little bit too far to round off. But usually in situations like this, you'll be able to tell how to scale them up accordingly. So for example, if you get a number that ends with 0.5, if you double everything, that will then get you whole numbers. Hopefully you shouldn't have to worry too much about odd cases like that. I think in Chem 103, usually most of the examples you're going to see are going to be pretty straightforward like this, where doing that math trick where you divide everything by that smallest number, you should hopefully get a whole number ratio. It's just that, in the off chance you don't, there are ways to get around that. Anyway, once you get down to a whole number ratio, well, now you've got your empirical formula. There's one carbon, two hydrogens, and one oxygen here that we're dealing with. That ratio is 1 to 2 to 1, and therefore your empirical formula is just going to be CH2O. All right, that's great. There's your empirical formula. But now we want to figure out the molecular formula. To do this, this is where that mass of our lactic acid, the molar mass, is going to come in handy. Before we use that, first let's figure out the mass of the empirical formula. So look up carbon, hydrogen, and oxygen in your periodic table. Carbon's 12, each hydrogen's 1, but keep in mind there's 2 of them, and each oxygen's 16. So when we add that up, we get about 30 grams per mole. Okay, well, if our mass of that is 30 grams per mole, but the molar mass of our formula is 90 grams per mole, how many times does our empirical formula fit into our molar mass? Well, 30 goes into 90 3 times. So if you want to see that, you just take your molar mass from the question, which was 90 grams per mole, divide by the molar mass of our empirical formula, which is 30, and you get 3. So that tells us that our molecular formula is 3 times our empirical formula. So therefore, we take our CH2O multiplied by 3, and the molecular formula for lactic acid is C3H6O3. Right? We just take each of our subscripts and multiply by 3. So please note for a carbon and oxygen, the reason there is no subscript is because the subscript's 1. Well, 1 times 3 is 3. Okay? All right, so that's how you go from from percent composition data to a empirical formula, and then how you can scale that empirical formula up to a molecular formula. Okay, and of course, like I said, if you're given a molecular formula and you want to scale down to an empirical formula, that's really straightforward. Like if you see 3, 6, and 3, you know that all 3 of these numbers are divisible by 3, and if you divide them by 3, you get CH2O. Okay, so yeah, so going in either direction hopefully should be pretty straightforward that way. And so that brings us to stoichiometry. Stoichiometry is how we keep track of amounts of chemicals in the course of a chemical reaction. In order to understand this, though, we first need to begin with the concept of the law of conservation of mass. What this means is that when a chemical reaction occurs, we don't create or destroy matter. The same amount of material that's in our reactants is present in our products. What is happening is that you are breaking and forming chemical bonds, you're rearranging the atoms that make your compounds, but the important thing here is that the atoms themselves are still the same. Okay, and as a result, the mass of those atoms is still the same. Now, all of the things we're going to do with stoichiometry are possible because of this law of conservation of mass. So as a result, we can kind of trust it to ensure that our calculations will turn out the way they do, because the law of conservation of mass is something that happens. So basically, the amount of material does not change. So since we know that it's not going to change, if we decide to examine just a part of it, let's say just one reactant, or tying it together with one product, or let's say comparing 2 products, we know that that relationship between them is going to be the way it is laid out in the chemical equation. All right, this is the reason why we balance equations, actually, to kind of show this relationship between chemicals. All right, let's see an example so you can, I'm kind of speaking kind of abstractly here. Let's see an example so you can see what I mean by this. So here we have an unbalanced equation. We have methane reacting with oxygen to make carbon dioxide and water vapor. So this is a combustion reaction, and we can balance it like we would any other reaction. So seeing that we have oxygen present in both of our products, I would balance carbons and hydrogens first. So feel free to pause this if you'd like to balance it yourself. But moving on, you can see that we have one carbon on the left and one carbon on the right, so we don't need to change that coefficient yet. We have 4 hydrogens on the left and only 2 on the right, so let's double our number of waters. And then accordingly, you should hopefully be able to figure out that you need 2 oxygen molecules on the left to balance out the 4 oxygen atoms on the right. Okay, because you need 2 times O2 to give you 4 oxygen atoms. Now, if you want to visualize this, let's look at this in terms of actual molecules. Right? And you can see again why we balance equations, right? We can't create or destroy atoms, so we put those coefficients to show that we have the same numbers of atoms on both sides of the equation, right? So over here on the left we have 1 carbon, on the right we have 1 carbon. On the left we have 4 hydrogens that are attached to our methane. On the right we have those same 4 hydrogens, except they're part of water molecules now. And on the left we have 4 oxygen atoms in our 2 oxygen molecules. And on the right we have 1, 2, 3, 4 oxygen atoms again, okay, between our carbon dioxide and our waters. So again, we've seen this already earlier in this chapter. We want to balance the numbers of atoms on both sides of the equation. Okay? Now, if we were to scale this up, we would see that this still holds true. We have 1 methane reacting with 2 oxygens to give us 1 carbon dioxide and 2 water molecules. If I scale this up to, let's say, if I had 100 methanes, they would react with 200 oxygen molecules to give us 100 carbon dioxides and give us 200 water molecules, right? Or I could scale this up in terms of moles. If I had 1 mole of methane, it would react with 2 moles of oxygen to give me 1 mole of carbon dioxide and 2 moles of oxygen. Okay, so again, my point here is that we can scale this up accordingly. And in addition, we'll see that the law of conservation of mass is held when we look at the masses of these compounds. All right, so if we were to scale this up to moles, and using our periodic table, look up the molar masses of the chemicals involved, we would see that the mass on both sides of the equation add up. Again, that makes sense because the atoms themselves add up. So it makes sense that the mass of those atoms would also add up accordingly. All right, so if we took the mass of 1 mole of methane and the mass of 2 moles of oxygen, it would come out to a little over 80 grams. Likewise, if we took the mass of 1 mole of carbon dioxide and the mass of 2 moles of water, we would also get that same mass. Okay. Now, the important thing to take away from here, because we can trust that this works out, we don't have to pay attention to all of the numbers because we know that the relationship between any 2 quantities are going to be tied together by the balanced equation. So I know that 1 mole of methane is going to give me 2 moles of water. Okay, if I want to compare methane and water, I don't actually have to care how much oxygen and carbon dioxide there is, because I can trust that this balanced equation tells me that for every 1 methane, I have 2 waters. Likewise, for every 1 mole of methane, I would have 2 moles of water. Okay, so essentially, we use our balanced chemical equation to tell us these relationships. Okay, and that's kind of the important thing that we are going to get out of balancing equations in this half of the chapter. All right, so let's use an example here, and you can see what I mean by this. All right, so here's another unbalanced equation. Let's go ahead and balance it. We have 1 carbon on the left and 1 carbon on the right, so that probably stays intact. We have 3 hydrogens plus a 4th one here on the right, so we're probably going to need a 2 over here to give us 4 hydrogens on the left. And we have 1 oxygen on the left and 1 oxygen on the right, so oxygens are balanced. So here's our balanced equation, where 1 carbon monoxide reacts with 2 hydrogen molecules to give us 1 methanol molecule. Okay. Now, The nice thing about these relationships is we can then scale them up or down, just like we did in my example earlier with methane burning in oxygen. We can scale these accordingly to whatever a question gives us. So for example, let's say we got a question that told us the amount of hydrogen, but didn't say that it was exactly 1 mole or 2 moles or anything like that. Let's say it was 0.295 moles, all right, some, completely different number. And the question asked us how many moles of methanol would be produced. Well, we could use the relationship between hydrogen and methanol to solve this problem. For every 2 hydrogens, there is 1 methanol. Okay, in other words, half the amount of methanol. So in the same way, if we had 0.295 moles of hydrogen, that would be cut in half, and that's the amount of methanol we would have. Okay, so this relationship between coefficients in a balanced equation show a molar relationship, or what we call a molar ratio, or a mole-mole factor. Okay, so depending on which textbook you're reading, there are different terms for it, but they are all the same thing. They're just the relationship between the moles of your compounds in your balanced chemical equation. Okay, and we're going to use them to get from one chemical to another. This is going to be the heart of every stoichiometry problem that we do. Okay, the steps before and after it might change, not just in this chapter, but even in subsequent chapters. This is going to be a step that we're going to see several times in our work. But this step of getting from moles of one chemical to moles of another chemical is going to be very important. So, the first thing we want to do is to be able to see those relationships. So, for example, if I were to compare my carbon monoxide and hydrogen, if those were the 2 chemicals I wanted to relate together, I would look at their coefficients from my balanced equation. Now, remember, if there's no coefficient, that's like saying that there's only 1 of that molecule. Okay, and likewise, if you scale it up, there's 1 mole of that chemical. So we have 1 mole of carbon monoxide for every 2 moles of hydrogen, because of that 1-to-2 ratio there. By the way, I'm only putting one of these conversion factors down. I could easily flip this. I could have said there are 2 moles of hydrogen for every 1 mole of carbon monoxide. Okay, now what other combinations do we have? Well, we could relate our carbon monoxide to our methanol. Okay, so again, look at their coefficients. There's 1 carbon monoxide and 1 methanol. So that's a 1-to-1 ratio. For every 1 mole of carbon monoxide, we have 1 mole of methanol. Or vice versa, we have 1 mole of methanol for every 1 mole of carbon monoxide. And of course, we could compare hydrogen to methanol. And it's a 2-to-1 ratio. There's 2 hydrogens for every 1 methanol. In other words, there's 2 moles of hydrogen for every 1 mole of methanol. Or vice versa. So, why don't we practice that? Here's an unbalanced equation for the combustion of water, of hydrogen to make water. Okay, or you could consider this the combination reaction that makes water. And so go ahead and balance this out, and then write out all the possible molar ratios for each of your chemicals involved in this chemical equation. Okay, so hopefully if you've balanced the equation, you should have gotten this. You probably realized that if there were 2 oxygens on the left, in my oxygen molecule, I probably need 2 water molecules. And then, accordingly, because you have 4 hydrogen atoms, you would need to double the number of hydrogen molecules to give you 4 hydrogen atoms on the left. Okay, now that you've got a balanced chemical equation, now you can look at those coefficients. So hopefully you should have seen that 2-to-1 ratio between hydrogen and oxygen. Okay, and in this answer slide, I've shown the other conversion factors as well. So basically, I flipped this. You could have 1 mole of oxygen for 2 moles of hydrogen as well. Okay, so go ahead and continue this and write out the different other combinations. So hopefully you should have gotten 2 moles of hydrogen for every 2 moles of water, and vice versa. It comes to the same thing. A quick note here before I move on. I've written 2-to-2 because those are the coefficients here. You can simplify this ratio. 2-to-2 is the same as 1-to-1. So, feel free to do that if you like seeing your fractions simpler like that. From a math standpoint, it's not going to matter. when we do the math, it's whether you multiply and divide by 2 or multiply and divide by 1, you're still going to get the same answer at the end. So it's really just bookkeeping, whichever you find easier to think in terms of. Okay, and then the last one there is oxygen to water, and that's a 1:2 ratio. Or if you do that backwards, 2 moles of water for every 1 mole of oxygen. Okay, so again, the key thing to get out of this is that we can only really compare 2 chemicals at a time. So whenever you have a question, a stoichiometry problem, you're always going to be asked to go from one chemical to another. Okay, it's always going to involve these two, like just 2 chemicals that you're comparing at a time, because that's really all you can relate in one conversion factor. All right. If you have more than 2 chemicals involved in the problem, there is an extra step you've got to take, and we'll get into that in a little bit. That's what we do in limiting reactant problems. All right. First, let's worry about comparing 2 things at a time. Okay. These conversion factors, of course, will help you do that conversion you need. The question will give you a particular chemical. They'll give you information about a chemical, and they'll ask you information about a different chemical. You want to make sure that you select the conversion factor, just like any other conversion factor, with the quantity you're given on the denominator and the quantity you want on the numerator. Okay, so make sure you put the coefficients of those chemicals in that order so that you get moles of those chemicals to cancel out accordingly. Okay, so like I said, this is the heart of every stoichiometry problem. Okay, this is going to be that central step. If you want to try out and just see how we would do this with that previous example with methanol, I believe we had 0.295 moles of hydrogen. Okay, in that earlier question, we were told that we have 0.295 moles of hydrogen, and the question asked how many moles of methanol would we get from that? Okay, that's the question mark here. So when we want to pick our conversion factor, we would select one that had moles of hydrogen on the bottom and that had moles of methanol on top, because that's the chemical we want. Okay, so the numbers that would go here would be those coefficients of those chemicals in that balanced equation. So just to jog your memories, rather than go back all those slides, I'll remind you that the equation was carbon monoxide reacting with hydrogen to make methanol. Okay, and there were 2 hydrogens for every 1 methanol. So we're going to take those coefficients. Okay, so there's no number written here, so you know it's kind of a unwritten 1. But we're going to use that 2 and that 1 in our molar ratio, or mole factor. So there's 1 mole of methanol for every 2 moles of hydrogen. Well, that gets moles of hydrogen cancel out, and we're left with moles of methanol as our answer. Okay, but what we would do to get that answer is we would take 0.295 and multiply by 1 and divide by 2. Okay, and that would give us the answer. So, like I said, this is the heart of every stoichiometry problem. No matter what information is given to you before and after the problem, at the center of it, you're essentially getting from moles of chemical A to moles of chemical B. And to do that, you need to know that relationship from your balanced chemical equation. All right. Now, quick note here. The only way to do these stoichiometry conversions is in terms of moles. There actually is no direct way to go from grams of chemical A to grams of chemical B. Okay, so that's something to keep in mind, but we'll cross that bridge when we come to it. We'll do problems where we start with grams and have to wind up with grams of something else. Okay, let's start out with just a molar problem. So, calculate the moles of carbon dioxide formed when 4.3 moles of propane react with excess oxygen. So here's the unbalanced equation. So remember, if you don't have a balanced equation, you need to balance it in order to do this problem. So, if you want to get some more practice at balancing, feel free to pause this video and try this out by yourself. Okay, but again, you probably noticed we've got 3 carbons on the left, so we're probably going to need 3 carbon dioxides on the right. Likewise, there are 8 hydrogens here, so my first step, a subsequent step would be to say, well, I probably need 4 water molecules to give me 8 hydrogens on the right there. 4 times 2 is 8. Okay, and then based on my number of oxygens, I can then figure out how many O2s I need. So hopefully you got this as your balanced chemical equation. Okay, now you've got to balance the whole equation because that's the only way you can check your work. But this question only involves 2 compounds. It involves carbon dioxide. That's what we're trying to find out. And it's giving us information about propane. The question tells us there's 4.3 moles of propane. Now, the question mentions that the propane is reacting with excess oxygen. The reason it's telling us that we have excess oxygen is to tell us that we don't have to care about oxygen. If there's excess oxygen, it means that there's enough oxygen. We don't have to worry about it. That's all that means. Okay, so don't care about oxygen. We're only concerned with our 4.3 moles of propane. That's going to be important, that chemical, and we're trying to figure out the moles of carbon dioxide. So we're going to look at these 2 coefficients. These are the 2 that we want to compare because those are the 2 chemicals that this question is involving with each other. Okay, so let's write this out. Okay, so with that in mind, we have our 4.3 moles of propane that we're trying to get to carbon dioxide. So again, looking at that relationship between those two chemicals, we have 1 propane for every 3 carbon dioxides, which means we could write that as a 1:3 ratio, or to write the opposite conversion factor, a 3:1 ratio. So now think about what we need, right? We have 4.3 moles of propane. That's what we're starting with. So which of those conversion factors would get moles of propane to cancel out? Well, we want to pick the one that has propane in the denominator, so we're going to pick this one on the right here. So we take our 4.3 moles of propane times 3 divided by 1. Notice that gets moles of propane to cancel out and leaves us with moles of carbon dioxide. So 4.3 times 3 is 12.9 moles of carbon dioxide, and that's our answer. Okay, so again, that's how we can use our molar ratio or mole-mole factor to convert from moles of one chemical, propane, to moles of carbon dioxide, the chemical we want. Okay, that's great. So again, I have to stress here that this can only be used for moles. We can only use a molar ratio or a mole-mole factor for moles. If you try to use these molar ratios with masses, with grams, you will get the wrong answer. Okay, so it's very, very important that if you are given grams, you need to first convert it to moles before you can use your molar ratio. Likewise, if you want your answer in grams, you need to take your answer in moles and convert it. Now, how do we do that? Luckily, we figured that out earlier in this chapter. We saw that we can convert from grams to moles or moles to grams using the molar masses from our periodic table. Okay, so make sure that we use the molar mass or molecular weight of chemical A to get from grams of chemical A to moles of chemical A, because then at that point you can then convert to moles of chemical B, okay, using your molar ratio. And then of course if you need grams of chemical B, you can use the molecular weight or molar mass of chemical B accordingly. So a quick note here about our, when we're given a problem, we won't necessarily be asked to do all 3 of these steps. We're not necessarily given, you can be asked for anything along this pathway. So for example, let's say instead of giving you grams of chemical A, the question gave you moles of chemical A, and they wanted grams of chemical B. Well, you don't have to do this first step anymore, because the whole point of this first step is to get to moles of chemical A. If the question gives you moles, well, you're done. You don't need to do that first step. You can immediately skip to the part where you take your moles of chemical A, use your molar ratio, and get moles of chemical B, and then continue on with the problem. Okay. Likewise, let's say the question gave you grams of chemical A, but instead of wanting grams of chemical B, it only wanted moles of chemical B. Well, you would do the first step to get to moles of chemical A, do your molar ratio, and then you would stop there because you've got the answer. There's no need to go on to grams. Okay, so my point here is please pay attention to your units. Okay, you want to be very aware of whether you're dealing with moles or grams when you're dealing with problems like these. Because again, you can only use this molar ratio step if you have moles. Okay, so watch out for that. So another piece of advice I have for you here is normally you would write down units. I tell you, just get into the habit of writing down units. I want you to take it a step further when it comes to stoichiometry problems. I want you not only to write out units like grams or moles, but I recommend also writing down which chemical they belong to. I think it gets kind of confusing sometimes when you see that, here we have information that's in grams and here we have information in grams. Here we have information in moles, and here we have information of moles. So it's usually beneficial if you say grams of what or moles of what to avoid confusion between your different quantities. Okay, so just a piece of friendly advice there. Okay, so watch out for that. And again, I have to stress that please only use your molar ratios when you're dealing with moles. Don't use molar ratios with grams. So with that in mind, let's try a practice problem that, well, practices that. So we're going to use actually a very similar problem to the one we just did, using the same exact equation and, in fact, using the same chemicals. We have 96.1 grams of propane, and we're trying to figure out how many grams of carbon dioxide are produced. Okay, so we're still going from the same chemicals to the same chemicals. The only difference here is instead of giving us moles and asking us for moles, the question's giving us grams and asking us for grams. Okay, so we need to be ready to do the necessary conversions, but this is going to take more than one step. Okay, that to get from moles of one thing to another, that's that middle step, but we're going to have to do some stuff around that to get between grams and moles. So we're starting off with grams of propane. As we saw earlier, we need moles for our molar ratio. So our first step, our first starting point here, is to get from grams to moles. Okay, so remember, in order to do this, we need the molar mass of propane, of the chemical that 96.1 grams belongs to. Okay, so here's the formula of propane, C3H8. Think back to how we would find out the molar mass of that. So, go back to your periodic table, look up carbon. Okay, carbon is about 12 grams per mole, and hydrogen's about 1 gram per mole. Okay, so if we add up those masses, 3 times 12 is 36, 8 times 1 is 8. So we add that up, we get about 44 grams per mole. Okay, so using that number, we can convert our 96.1 grams into moles of propane. Okay, so let's try that out. So it's going to skip to that step. Here we go. So here's that first step. We've got 96.1 grams of propane. We want to divide by that molar mass to get grams of propane to cancel out and leave us with moles of propane. Okay, so when we do that, we figure out that we have, about 2.18 moles of propane. All right. So if we have that many moles of propane, now we're at the same starting point we were with the previous problem. We can get from moles of propane to moles of carbon dioxide by using the ratio of those two chemicals. We have 1 propane for every 3 carbon dioxides, or 3 carbon dioxides for every 1 propane. So we scaled it up to moles. There's 3 moles of carbon dioxide for every 1 mole of propane. So if we pick that ratio, we can get moles of propane to cancel out. And so we take our 2.18 moles of propane, multiply it by that 3 to 1 ratio. So multiply by 3 and divide by 1. And we get moles of carbon dioxide. Okay, and if the question wanted the answer in moles of carbon dioxide, we'd be done here. We could just give this answer and that would be it. But the question wants the answer in grams. So we have one more conversion to do. We've got to take our moles and convert to grams. But notice that this is moles of CO2. So we need to figure out the molar mass of CO2. So we look up carbon as, it's got a mass of 12 grams per mole. Oxygen 16, but there's 2 of them. So when we add them up, we get 44. Okay? And now this time we want to multiply by 44. And so, we take those two numbers, we multiply by that molar mass, so moles and per moles cancels out, and we get our answer in grams. Okay. Now, a quick note here about a big coincidence that you may have picked up on. All right, you're probably saying to yourself, "Wait a minute. If I took 96.1 and multiplied by 3, I would get approximately that answer, right? I thought you said you couldn't use that 3-to-1 ratio with grams. You can only use that with moles." And the answer is yes. There's a big coincidence here in that the molar mass of propane happens to be the molar mass of carbon dioxide, roughly speaking. That's actually why I went to more significant figures here to show you that they aren't the same number. The fact that they're so similar is just a coincidence. Okay, so to be honest with you, you're probably not going to come across a coincidence like this again. But I wanted to include an example that showed you that something like this is possible. Okay, so again, do not use that 3-to-1 ratio with grams. You can't go directly from here to here in one step. Okay, so just to recap, here are the 3 steps again. Okay, our first step was to go from grams of propane, the chemical we were given, to moles of propane. Again, still the chemical we were given, just in moles. Okay, then we use our molar ratio to go from moles of the chemical we were given to moles of the chemical we want. And then, of course, our last step is to go from moles to grams for that chemical, okay, and get the answer that in the units that we want. So, so those are your basic 3 steps. And again, that first or that third step might be optional, depending on what the question's giving you and what the question's asking you for. But that middle step of going from moles of the chemical you're given to moles of the chemical you want, every stoichiometry problem will involve this step. Okay, so be sure to watch your units and just get comfortable by multiplying by these ratios. Okay. Quick note here about ratios. I've set this up using our typical conversion factor method that we've used, from the first chapter onwards. Again, I think I told you back then, this is just bookkeeping. There are multiple ways to set up these types of calculations. If you learned a different method in high school or another class and you're more comfortable with it, by all means, feel free to pick that other method. You'll still get the same answer because you'll still be multiplying and dividing in the right places. Okay, so you can see here I've broken this down to 3 steps. I could have done this all on one line, right? I could have done this as one big calculation. Alternatively, instead of using conversion factors as fractions, I could have set this up as a ratio. Okay, so the ratio of carbon dioxide to propane is a 3-to-1 ratio, and I would then have x is to 2.18, and I would solve for x. Again, it's totally up to you, and based on how you like to set up these types of problems. Okay, the math works out the same no matter how you set it up. Okay, let's practice this out. Okay, so here's another practice problem. So go ahead and try this out. The nice thing about this one is that there's actually multiple things to practice here, and when you get your answers, you can sort of verify the law of conservation of mass. So here we have carbon monoxide and hydrogen reacting to form methanol. This is that equation I used to kind of begin our introduction to stoichiometry. So if you recall, when we balance this, we have 1 carbon monoxide reacting with 2 hydrogens to make 1 methanol. Now, the question asks, what mass of carbon monoxide and what mass of hydrogen are required to form 6 kilograms of methanol? Well, we're going to have to do this in 2 separate problems because, again, we can only compare 2 chemicals at a time. Okay, so you're going to have to pick either carbon monoxide or hydrogen and compare them accordingly to your 6,000 grams of methanol. Okay, so even though we've got 2 unknowns here, what this tells us is that there's actually 2 questions we're solving here. Okay, so break this down into 2 parts. So first things first, you want to take your 6,000 grams of methanol here and convert that into moles. Okay, but again, I'm kind of walk through this problem. Feel free to pause here if you want to try this out yourself. Okay, so if you're with me here now, let's walk through this problem. Okay, so that first step, like I said, well, once you know that 6 kilograms is 6,000 grams, we want to get that to moles. So we would divide by the molar mass of methanol. Now, again, I've gone to more significant figures here, but if you use 32, that's fine. Okay, but we want to divide by molar mass. That gets grams to cancel out, and that gives us moles. Okay, so if you got 32, by the way, it's just 12 plus 3 plus 16 plus 1. That's where that 32 comes from. Okay, so you get moles of methanol. Okay, first step's done. Now we want to get to our moles of the chemicals we're interested in. So again, we're doing this as two separate problems. Our first problem is to get to carbon monoxide. So what's the relationship between methanol and carbon monoxide? Well, it's a 1-to-1 ratio, right? There's one methanol over here for every one carbon monoxide. So if we have 187 moles of methanol, well, that tells us we have 187 moles of carbon monoxide, the same number, because of that 1-to-1 ratio. Okay, so that was a really easy calculation. That was great. What about hydrogen? Okay, so this is not the final answer, by the way. I'm just going to work hydrogen out too, though, just so we can all be on the same page here. Okay, stepwise. If we were trying to do this for hydrogen, what's the relationship between hydrogen and methanol? We've kind of seen this already before, but there's 2 hydrogens for every 1 methanol. So in other words, we have to double the amount. So instead of 187 moles of, we go from 187 moles of methanol to about 375 moles of hydrogen. Okay, so again, just double that number because of that 2-to-1 ratio. Again, though, this is not the final answer. The question wanted the answer in grams. So we would take those numbers and multiply by their molar masses. So carbon monoxide is 28 grams per mole, right? 12 plus 16. Okay, and so we'd multiply by molar mass to get moles of carbon monoxide to cancel out, and we get our answer in grams. Okay, and of course we can do the same thing for hydrogen. Hydrogen, remember this is a hydrogen molecules, H2, so that's about 2 grams per mole. So again, if you double that, you get that number in grams. Okay, and again, if you want to see the law of conservation of mass, if you add up these two numbers, you'll get approximately 6,000 grams, which is the amount of methanol that we started the problem with. Okay, so this kind of shows, illustrates the law of conservation of mass as well. Okay, so in that last question, we happen to have we had to deal with 3 different chemicals, right? We were given information about one chemical, and we were asked about information about 2 chemicals. And that told us that we had 2 questions, because it was asking us for 2 things, okay? Questions get interesting where they give you information about 2 chemicals and ask you about 1. Okay, that's kind of weird because there's no way to tie together 3 quantities using a conversion factor. You can only compare 2 things at a time. Okay, so when we get a problem like that, where they give us information about both our reactants, or at least 2 of them, and they don't tell us which one to use, what that's essentially telling us is that we've got what's called a limiting reactant problem. And effectively, we're going to just have to do 2 problems. We're just doing the problem twice, and we're going to figure out, based on our answers, which one's the right one. Okay, now let's understand why we have to deal with this problem. Okay, what do I mean by a limiting reactant? Well, when a chemical reaction happens, the reaction keeps on going typically until you run out of one of your reactants. Whichever reactant runs out, that kind of stops the reaction, and that's why we call it a limiting reactant. It limits the amount of product you can make. All right. The other reactant's called your excess reactant because you're going to have some of that left over when the reaction stops. Let me give you a silly example so you can see what I mean. All right. Let's say we are making hamburgers. All right. We open up our pantry. We have some bread. We have some patties, and we're going to make hamburgers out of them. All right. Now, just for stoichiometry sakes, we're going to say we use 2 slices of bread plus 1 patty to make 1 hamburger. Okay, we're treating it kind of like a chemical reaction here. And again, I'm calling this bread instead of a single bun, just to again get the that concept of stoichiometry built in here. Okay, so 2 slices of bread plus 1 patty gives us 1 hamburger. So we open up our pantry and we find out that we have 4 slices of bread and 3 patties. So my question to you then, of course, is how many hamburgers can we make? Okay, now this is a silly question because you're looking at this and you're like, well, obviously I can make 2 hamburgers, right? And I'd have a leftover patty. Okay, but how did you know that, right? Like, what was your brain doing to figure that answer out? Okay, well, we could try picking one of our reactants and saying, how much could we make from that? So if I ignore the number of patties, if I look just at my 4 slices of bread, how many hamburgers can I make from 4 slices of bread? Well, since 2 breads make 1 hamburger, 4 breads would make 2 hamburgers. Okay, so I can make a maximum of 2 hamburgers with my 4 slices of bread. Okay, now let's look at our patties and ignore the bread. With 3 hamburger patties, how many hamburgers could I make? Well, there's a 1-to-1 ratio between patties and hamburgers, so 3 patties would make 3 hamburgers. Okay. Now, which of those answers do I trust? Well, obviously the smaller one, right? I could have 1,000,000 patties. I'm not going to make 1,000,000 hamburgers if I only have 4 slices of bread, right? The smaller answer is the correct answer because your reaction stops once you run out of something. As soon as you run out of bread, you can't make any more hamburgers. That's why you have a leftover patty, because the patties are in excess. You are limited by the amount of bread that you had. That's why you could only make 2 hamburgers. Okay. So, same thing happens in chemistry, right? We pay attention to what our reactants can make, theoretically, and whichever answer is smaller, that's our limiting reactant. We know that the reaction is going to stop once that reactant runs out because that's the smaller amount of product we can make. Okay, so essentially, when you have one of these problems where they give you information about both your reactants and they want to know how much product you make, you essentially have to do the problem twice. You pick each reactant, figure out how much product you'd make, and then the smaller answer is the right one. So let's try a problem out like that. Okay, so again, just treat it like a regular stoichiometry problem. You're just doing it twice. So let's say we have lithium nitride, okay, and we are forming it from lithium and nitrogen. Now, we have 56 grams of nitrogen and 56 grams of lithium, and we are reacting them together, and we're going to figure out how much lithium nitride we made from that. So here's our chemical equation. It's unbalanced, so feel free to balance this if you like. Okay, and you need to balance it in order to proceed with the problem, so feel free to pause this, I should say, if you want to balance it. But if you want to balance it with me, you can see that I've got 2 nitrogens here, so I'm probably going to need 2 lithium nitrides since there's only 1 nitrogen on this side. And then, of course, that will control how many lithiums I make. So when you're done balancing, hopefully you got that. You should see that I've got 6 lithiums on both sides. 2 times 3 is 6 there. And 2 nitrogens on both sides. Okay, so again, the question tells us we have 56 grams of lithium, 56 grams of nitrogen. How much lithium nitride do we make? So let's do this one chemical at a time. Let's start with just our 56 grams of lithium and ask how much lithium nitride can I make from those 56 grams of lithium? Okay, so let's start off with that. So we've got grams of lithium, so our first step, of course, is to get to moles. So look up lithium in your periodic table. And you probably figured it out, it's about 7 grams per mole. We've got a few other quantities in here that's going to be, going to come in handy for the rest of the problem, but let's skip on ahead to the actual solving of the problem. So there's our first step. We're going to take our 56 grams of lithium and divide by that molar mass, because again, we want grams to cancel out. So remember, when you're going from grams to moles, divide by molar mass. And we're going to get about 8 moles of lithium. Okay, now of course, we can't stop there because the goal is we want to know how much lithium nitride we're going to make. So let's look at the relationship between lithium and lithium nitride. There's 6 lithiums for every 2 lithium nitrides. So it's a 6 to 2 ratio or 2 to 6 ratio. Or if you want to simplify that, you could say 3 to 1 or 1 to 3, but I've used the actual original numbers here. So I'm going to multiply by 2 and divide by 6, because again, I want my moles of lithium to cancel out, and it's moles of lithium nitride I want. So I'm going to put those coefficients from that balanced equation that correspond to those chemicals. There's 6 lithiums in my balanced equation, and 2 lithium nitrides from my balanced equation. And that's why I put those numbers where they are. And there I get moles of lithium to cancel out. So if I take my 8 moles of lithium times 2 divided by 6, I get about 2.7 moles of lithium nitride. Okay, again, there's going to be a little bit of rounding error here if you use 7. Here in my calculations, I've used the actual numbers. Again, if you round it off to 7, that's totally fine. Okay, you get a close enough answer. Okay, so that's how many moles of lithium nitride I would get if I use all 56 grams of my lithium. Now, I could go on and calculate grams of lithium nitride too, but in order to compare my numbers, it's sufficient to compare moles of lithium nitride. So let's just stop here temporarily, and let's move on to the nitrogen and see how much lithium nitride we can get out of that. Well, we've got 56 grams of nitrogen. Of course, we can't stop there. We want to convert to moles of nitrogen. So look up nitrogen in your periodic table, and you'll see that the element nitrogen is 14 grams per moles, but keep in mind that nitrogen molecules are N2, so we've got to double that, so that's 28. So we take our 56, divide by 28 grams per moles, and we get about 2 moles of nitrogen. Now, what's the relationship between nitrogen and lithium nitride? It's a 1 to 2 ratio. We have 2 lithium nitrides for every 1 nitrogen. So our 2 moles of nitrogen give us 4 moles of lithium nitride. Okay, again, don't mind the slight rounding errors here. But basically, we're going to get about 4 moles of lithium nitride, okay, if we react all 56 grams of nitrogen. So, which one is our limiting reactant? Our lithium gives us 2.7 moles of lithium nitride. Our nitrogen gives us 4 moles of lithium nitride. And remember, it's the smaller answer that's the correct one. Okay, so that tells us that lithium is our limiting reactant or limiting reagent. And therefore, we have to use this answer when proceeding with the problem. You can ignore this answer, okay, for our nitrogen, all right? Because this is our limiting reactant, this is the one we're going to use to proceed with the problem. This answer here doesn't matter, okay, because this is excess. So that's our excess reactant. That means we don't have to care about it anymore. Okay, this you could have like a ton of excess reactant. It doesn't matter. It's not going to form any product. So let's proceed with the problem. Well, the last step, of course, is to go from moles to grams of lithium nitride, and for that you need the molar mass of lithium nitride. So if lithium is 7 times 3 is 21, plus the 14 for the nitrogen gives you 35 grams per mole. Okay, and I've used the more precise number here, but again, if you use 35, that's fine. You get a close enough answer. Okay, so we're going to multiply by molar mass, so that gets moles to cancel out, and you should get somewhere in the ballpark of 94 grams of lithium nitride. Okay, so that's how we do that problem. So essentially, we did the same 3 steps we always do. It's just that we had to do it for each of our reactants and then pick the smallest answer. Okay, so that's really all you do with a limiting reactant problem. Okay, make a note of this 93.7 grams of lithium nitride. I'm going to use that in a later problem to illustrate a percent yield. Okay, so we'll come back to that later. All right, so that brings us to percent yield. Whenever we do these calculations, you have to realize that these are just calculations. They're kind of theoretical. They're what we would get if everything went perfectly. But real life is not perfect. If you were doing these these reactions in your lab, not everything would go according to plan. You have sometimes you spill stuff. You lose little amounts of reactant or product. Sometimes not all of your reactant reacts, right? Sometimes you have side reactions where your reactant makes something that's not the product you want, or something that gets lost. These things happen, and so you don't always get the amount of product that you calculate. Okay, so that's something to watch out for. So we called the product, the amount of product that we calculate, that's known as our theoretical yield. Okay, if you do an experiment in lab, what you get is called your actual yield. Well, in order to see how successful that experiment was, we do what's called a percent yield calculation. Okay, now my analogy here is picture a basketball player. Okay, let's say this basketball player gets fouled 10 times in a game, or well, it goes to let's say they're shooting 10 free throws, so I guess they're fouled 5 times in the game. But anyway, they're shooting 10 free throws in the game. Theoretically, they should make all 10 of their free throws, right? Like that's why you practice free throws in practice, so you can make them in a game, right? But let's say they only make 8 out of their 10 free throws. What's their free throw percentage? Well, you'd quickly say, oh, it's 80%, right? They made 8 free throws out of 10 possible free throws. 8 divided by 10 times 100%, that's 80%. Well, that's exactly how percent yield works. We take the actual yield that that we get from the experiment. We divide by the theoretical yield, what our stoichiometry calculations give us, and times it by 100. And that tells us what the percentage is and how successful that reaction was. So, remember how we had 93.7 grams of lithium nitride in that previous problem? Well, again, that's a theoretical yield, right? We should get 93.7 grams of lithium nitride if our 56 grams of lithium reacts. Now, let's say someone does this reaction, but they only get 90.8 grams of lithium nitride from their reaction with 56 grams of lithium. So what was their percent yield? So we take their actual, which is 90.8, divide by their theoretical, which was the 93.7 grams we got from our calculation earlier, times 100, and that's a 96.7% yield. Okay, so that's how you do a percent yield. Okay, now please note that this question gave us the numbers kind of directly, right? We had the question tells us the actual yield. We had the theoretical yield on hand, and so it was easy to plug them into this formula. Okay, keep in mind that might not always be the case. Sometimes the question might give you information about the reactants you're dealing with. Please note that this is grams of product. This is grams of lithium nitride. This is also grams of lithium nitride. You have to have the same chemicals in this equation for this calculation to work out. Okay, you can't have grams of product for one of these numbers and grams of reactant for another one of these numbers. You just can't compare them like that. Okay, so please keep in mind that sometimes you may have to actually do a stoichiometry calculation first to get this theoretical answer. Okay, so please keep that in mind when you're doing a problem like this. Okay, so please be wary of what the question gives you. Okay, so it might give you information about your reactants. You have to figure out the theoretical amount of product using a stoichiometry calculation. All right, that brings us to the last topic in this chapter, and that is energy in chemical reactions. Okay, so I've mentioned that chemical reactions happen when we break and form bonds between atoms. Okay, so we break our bonds in our reactants, we shuffle the atoms around and form new bonds in our products, right? And that's basically a chemical reaction in a nutshell. Now, it turns out that breaking bonds costs energy. Okay, you need to provide energy to overcome those attractive forces between atoms. Likewise, forming bonds releases energy. And it's the imbalance of the bonds you're breaking and forming that results in a net change in energy for your reaction. We call this change in energy for a reaction enthalpy change, and it's represented by the symbol delta H, okay, where delta is the change in our quantity. H here stands for enthalpy. All right, so enthalpy is just the heat that's either produced or used up in a chemical reaction. So if you want to see what this looks like, we have these what we call energy coordinate diagrams down here. I'll explain more in detail what the different parts of this mean, especially what activation energy is in a later chapter. But for now, I want you to pay attention to the difference between our reactants and our products. Okay, so if your reactants have more energy than your products, if your products are more stable and they have a lower potential energy like this, that change in energy has to go somewhere. This energy is released into the surroundings. So if we're going from a higher number to a lower number, okay, remember that's a negative change. So delta H for this would be a negative number. We call that an exothermic reaction. It's exothermic. Exo means outwards, and therm, of course, refers to heat, because when this happens, heat is given outwards. So a good example of this would be a combustion reaction. So combustion reactions, when you burn something, you get a lot of heat from it, right? It feels very hot. That's because the carbon dioxide and water vapor you're producing is relatively low in energy compared to the high energy reactants that you're burning, that fuel that you're burning, and that heat that you're feeling is the difference in that energy, okay, and that potential energy between those chemicals, right? When you take into account the bonds you're breaking here and the bonds you're forming. You could also have the opposite situation where your products have a higher potential energy and therefore they have to absorb energy when they form. We call this an endothermic reaction. So endo, of course, meaning inwards. Okay, so an endothermic reaction is one where delta H is positive and therefore heat is absorbed by the reaction. Okay, so you can tell an endothermic reaction is going on because it feels cold. Okay, it's sort of sucking up heat from the surroundings, including from from your body. Let's say you're holding onto a beaker in which an endothermic reaction is happening. It'll feel cold to your touch because that reaction is taking heat away from your hand that you're holding the beaker with, and that's why it feels cold. All right. So again, remember the difference between exo, which means outwards, and endo, which means inwards. Okay. So like crustaceans and insects have an exoskeleton. Their skeletons on the outside of their body. We have an endoskeleton. Our skeleton's on the inside of our body. Okay. So if that helps you remember the difference between exo and endo. Right, so let's have a look at what this means for us. Okay, so here's an example of a reaction. We're going to pay attention to the delta H for it. So let's say we have a photosynthesis reaction. For those of you who haven't taken biology before or aren't familiar with this, photosynthesis is how plants produce energy. So they take carbon dioxide and water, and using chlorophyll and sunlight, they convert that into glucose. Okay, and that glucose is a carbohydrate that they use for fuel. Okay. Now, if you look at the delta H for this reaction, well, you could probably figure out what it's going to be just by knowing what's required for this reaction to happen. I mentioned earlier that you require sunlight for this to occur, and so that should tell you that this is an endothermic reaction. It absorbs energy from the sun in order for this reaction to proceed. Okay, and you can see here that our delta H is positive 2,801 kilojoules for every mole of this reaction. So for every mole of glucose produced, we absorb 2,801 kilojoules of heat energy. Okay, now what about the reverse reaction? Metabolism. If we were to take glucose and burn it in oxygen to make carbon dioxide and water. This is what happens in cell respiration. Okay? Is this process going to be endothermic or exothermic? Well, you've probably figured out it's exothermic, right? If this is how cells get energy. But how much energy is involved here? What's delta H for this reaction? Well, it's just negative 2,801 kilojoules per mole. So that's because, again, the bonds that you were breaking in photosynthesis, you're forming in metabolism, and vice versa. Okay, so because it's the same bonds involved, it makes sense that the signs just flipped. All right. Now, you probably noticed I said that this is for 1 mole of the reaction. I was talking about glucose here because there's 1 mole of glucose in this balanced equation. But you could have used any of these chemicals to figure out that tie-in to this number here. So you could have tied this into every 6 moles of carbon dioxide. And likewise, you can scale this up or down depending on how much material the question says that you have. Okay, so let's try a problem that deals with that. So let's say we were looking at the combustion of sulfur dioxide. So sulfur dioxide reacts with oxygen to make sulfur trioxide. And here's the balanced equation. Now, we're told that delta H for this reaction is negative 99.1 kilojoules, which makes sense. It's a combustion reaction here, so it makes sense that we have a negative delta H. It's an exothermic reaction, as most combustion reactions are. Now, instead of having 2 moles of sulfur trioxide, the question's asking us how much heat's produced when 75.2 grams of sulfur trioxide are produced. Okay, so note that looking at that chemical, sulfur trioxide, if there's 2 moles of sulfur trioxide, we release 99.1 kilojoules. If we have 75.2 grams of sulfur trioxide, what is the amount of heat? Okay. So first, right off the bat, you probably noticed that we're not comparing apples to apples here. We've got apples and oranges. We've got grams of sulfur trioxide in the question, but our equation, of course, has moles. So we probably want to convert our grams to moles here. Okay, so at some point you're going to need your periodic table, and you're going to have to look up the mass of sulfur and oxygen. Okay, so hopefully you figured out sulfur is 32, each oxygen 16, though please note that sulfur trioxide has 3 oxygens, so you're going to have to take 16 times 3, or 48. Okay, and so you're going to keep that 72 in mind, for 72 grams per mole in mind for the calculation you're doing. So we're going to start off with grams of sulfur trioxide. Using the molar mass, 72 grams per mole, we want to convert to moles of sulfur trioxide. And then, of course, we're not done there yet, right? Because we want to take the information from our question, our delta H for this reaction, and we want to figure out how much heat is involved for this particular reaction. So to get those quantities, those conversion factors, I mentioned earlier, I said 72, I meant 80, sorry. We have 80 grams per mole of sulfur trioxide, okay? Right, again, 32 from our sulfur plus the 48 from our 3 oxygens, that adds up to 80 there, okay? And so, again, we can have one of 2 conversion factors. We could have 1 mole per 80 grams or 80 grams per 1 mole, okay, depending on which one will get us from grams to moles. And of course, from our balanced equation, we saw that 2 moles of sulfur trioxide gives us 99.1 kilojoules of heat released. So again, we can put that as either one of these conversion factors just by flipping that fraction. Okay, so think again which one you want to pick that would convert moles to kilojoules. Okay, so which one of these 2 conversion factors will get rid of moles? Okay, so remember, whenever you want to get rid of a unit, you want to pick the conversion factor that has that in the denominator. So we're going to divide by molar mass to get grams to cancel out. And then we're going to multiply by 99.1 kilojoules for every 2 moles. Okay, so now notice that this one's a little bit different in that there are numbers in both the numerator and denominator. So keep that in mind. So we're going to take our 75.2, divide by 80, multiply by 99.1, and divide by 2. And that should give you 46.5 kilojoules. Okay, and again, this is just one way to set up the problem. If you like setting up ratios, this is another one of those problems where setting up ratios is totally acceptable. Okay, again, however you choose to set up this problem, as long as you're multiplying and dividing the numbers in the right way, you're going to get the right answer. Okay, so that's it for this chapter. So please note we have a lot of practice problems. There's a reason for that. You probably noticed we did a lot of procedural things. So the more you practice it, the easier this will get. Okay, so please do try this practice out. And that's all I've got for you. So yep, good luck preparing for the quiz, and let me know if you have any questions.